All right, so we're talking about means, right? So how we extract model means. And notice again that the function here means is not going to tell you, I mean, I guess it does tell you that you shouldn't do this. Because when you run, I'm just going to wait for mine to finish running, but when you run here, it does tell you, note results may be misleading due to involvement in interactions. Basically telling you, watch out, because if you're just getting your main effects, that may not be telling you the whole story. So it's going to warn you. It's not going to stop you from doing it. All right, so this is how you would get the means for nitrogen rate by itself. As you see, it gives you like the levels, it gives you the actual EM mean, the expected marginal means from the model, and then some more information there as well. Now, we want the interaction. I want to show you the one of the ways to get a two-way interaction and its means, which is just to use the colon symbol here and then do potassium rate kilograms per hectare. So we're basically saying, give me the interaction between nitrogen and potassium. If we do this and we print it, we get so we get now more cells because it's all the 9 means between nitrogen and potassium. We get the mean values right there. And you may notice that there's no structure here in the sense that it's everything being compared to everything, or not compared yet, but just the means of everything without any structure. I do want to move to the next chunk here, which I left you the code already. I'm going to quickly tell what's going on here as we talk more about this in the CRD exercise. So now that we got the means, we want to do pairwise comparisons. This is the goal of an analysis of variance, is to get the pairwise comparison. So I'm giving here, we're using this function called CLD, that stands for compact ladder display. We're given the models, RCB, or I'm sorry, not the model, but the means that we just created above. So RCBD means all, that's what we're given to CLD. I'm changing a few arguments here. You can read the documentation of the CLD function if you want to know more. But basically, I'm asking for the order to be reversed because I think it does from the smallest mean to the highest, and then it gives A to the smallest. In our case, higher is better. So for me, it makes sense to put A on the highest number, on the highest yield. So that's why I'm asking reverse equals true. This adjust argument is if you want to use any adjustments. I'm asking to use no adjustments, but like if you heard of things like Tukey and Donuts, and I mean, there are many other adjustments. This is where you would say that you want the name of that adjustment. If you ask for help of CLD and go through the documentation, it's going to show you what options you have to change on this argument here. And then I think it gives numbers rather than letters. So instead of putting A, B, C, it puts 1, 2, 3. And so I'm just asking here to give me letters instead. That's what I'm doing. So go ahead and run this chunk and print that.
Professor, sorry, can I ask a question here? It's relevant here. So here, adjust, can you share like when should we use any adjustment at all?
Yeah, so this, I mean, in my opinion, it really comes down to your planning of what comparisons you're making and also what is common in your specific area, right? So so what happens is if we choose to do an adjustment, any adjustment is gonna make it harder to find statistical differences between treatments. There is a reason to using adjustments. If you have never heard of this is not a class you're going to fully learn that. I can make a quick comment that what happens is the more comparisons you make, the more false positives you find. Meaning that if I do 3 comparisons, so I'm probably fine there. But if I do 100 comparisons, probably the rate of those 100 comparisons, that would be false positives in the sense, meaning that it found a difference, but there really should not be different in terms of letter separation. The more comparisons you make, that rate of false positives increase. And if you use no adjustment, you're not controlling for that. If you use some level of adjustment, you're basically making it harder for the model to find difference between treatments, and that happens because you're trying to control for that false positive rate. So decreasing so basically, I mean, we can even check here. So adjust right now, I have no adjustment being applied. I think that if I want two keys, just say two key. Let's see if that. Okay, so it's actually saying it has Tuki, but it's saying that it was changed to SIDAC because Tuki is only appropriate for one set of pairwise comparisons. All right, it's an opinionated function, I guess. So here we see that now we have so one A, a lot of A B's, and then three B's. If I go back to none, this is different. It's gonna be, I'm gonna find more differences if I have. So see that now goes all the way to E, meaning that if I have no adjustment, it is the model finds more differences. And if you apply an adjustment, the model is you have to have larger differences between treatments or a smaller standard deviation or standard error to be able to find a difference. And Umar, asking your question more directly, again, I think what I would do is check your literature and see what people do. Some areas have very specific, types of adjustments. Tukey is the most common, so we can use that. Normally, the recommendation is if you are doing comparisons that you plan to do even before you look at the data, that it would be okay leaving none or even using Tukey, which is one. It is a restriction, but it's one of the least restrictive adjustments. Tukey. There are some others that are going to be more restrictive and be harder to find differences. And those are normally recommended to do if you're doing comparisons you did not plan to do from the beginning of the study. Like you look at the data and you said, maybe if I use something less restrictive, I would see a difference. So you're like p-hacking to some extent. Yeah, I mean, you shouldn't be doing that anyways, but yeah, you have that choice here based on if your comparisons were already planned and also based on your specific literature. I use Tukey and I use no, because really, so one thing that's interesting to talk about, and I don't think it's very clear, you've probably seen on papers people saying that they use the Fisher's LSD, for example, as like their mean comparison method. What Fisher LSD means is pretty much that they did not use an adjustment. They basically just decided how to break down their comparisons based on the ANOVA table. That's it. Because really, I want you to notice something here. There is nothing keeping you from running a model and going straight to means. We check the ANOVA table because that's part of the process. But there's no stop sign. There's no barrier that keeps you from going straight from LM to EM means. You can do that if you want. I mean, I wouldn't recommend it. Nobody does it. But you could. There's nothing stopping you. So when people say they use Fisher's LST, it basically means that their adjustment was to first look into the ANOVA table, and then based on the ANOVA table, then they decided how to break down means. That's what Fisher's LST means. So that would be like one not adjustment, but one check, right? I'm not getting all means possible. I'm just getting the means that were significant in my ANOVA table. That made sense for me. Yes.
So going back to what we were talking about before, like what does it mean for a grower if you're using an adjustment or not, and it's significant on non-adjusted 50 to 100 pounds per acre nitrogen versus being significant? Like what does that mean for a grower? Or
Yeah.
What implication?
That's a great question, right? So, I mean, the implication that is going to have, so Jonathan was asking here, what's the implication to a grower, whether we choose an adjustment or not? So really the adjustment is one of the ways that we say, I have this level, or I want to have some level of certainty about telling somebody that this is different or not different, right? If you think of it, there are two ways one could p-hack an analysis. I mean, many ways, but two of them directly to this example here is you could change a couple of things here. Sorry that I'm scrolling a lot, but so you could change your adjustment. You could also change your alpha level, right? So right now, the default alpha level here is 0.05. It tells us here. I did not have to specify because that's the default, but I could come here and use an alpha of 0.1, which makes it more liberal, easier to find differences, right? I could do that, and I'm going to find more differences most likely. Interesting. Actually, it looks different than what I was expecting, but yeah, it's less for some reason. But you can play with alpha, right? Normally, I mean, 0.05 is a default. Sometimes people use 0.1, especially if you have like on-farm trials that are the highly variable. You have more variability. You know you're gonna have more noise, and you want to. And also something that it comes into play is, for example, if people like in breeding, plant breeding, animal breeding, they may have like thousands of varieties, right? You really don't care if you say that these two are different when they're not, if they're on the top, right? So let's say I have 1,000, I want to select the top 50. I would not use an adjustment just because I really don't want to cut myself short at this level of the process, right? So I will make it more liberal and incorporate things that perhaps are not among the top 50, but at least I don't cut myself short so early in the process of saying, I'm going to discard these because I use 0.05 and took the adjustment, So there's a lot of things at play. The recommendation that I follow, that I think most people follow, is just to determine these beforehand. Maybe based on the area that you're working on, the reading papers, you were going to realize, I mean, if you go to on-farm studies, it's somewhat common to find alpha 0.1 and no adjustments. But maybe perhaps if you go to medical sciences where, people's lives are at stake, maybe they want to be extremely conservative, right? And really use like the hardest adjustment they can in 0.01 even, right? So it really area dependent. In agriculture, I would say using no adjustment or Tuckey's adjustment, which is a slightly more restrictive adjustment, is common, and then 0.05 is the default alpha level, but you see 0.1 as well, depending on the goal. Did that answer?
Right.
Okay. I think somebody had a question online. I saw a hand go up.
Yeah, I was about to ask the same question, like, does that none means fishes LSD or none means nothing, something like that?
Yeah, the none means that you're not doing an adjustment, which if you report these means, it would be Fisher's LST. All right, I'm gonna, go back to my alpha 0.05, which was the default. And no adjustments. But then again, this is up to you and to your area of expertise. What I do want to notice here is, so we got the means, everything by everything else, no structure in the way we got the means, and that structure, or that lack of structure perhaps, that we created on the EM means level trickles down to CLD. So here we're comparing everything against everything else, right? So for example, is it interesting to me as a researcher to know that 0 nitrogen 60 is different from 200 nitrogen, 0 potassium? Maybe it is, maybe it's not. So it comes down again to your question, to your hypothesis, and your goal with this study. I'm showing you this because this is one of the 3 possible ways you can get means and pairwise comparisons in a 2-way interaction. So now we're going to just revisit a little bit with what Umar was saying. So let's say that really I wanted to know the effect of nitrogen rates inside each potassium rate. And I think once we do it, I think it's going to be easier for you to understand than just me saying these words. So if I want to know the levels of one factor, how they compare inside each level of the second factor, you would use the vertical bar symbol. So N rates, vertical bar, potassium rates. This would do all nitrogen rates inside each potassium rate separately. If you run that and you print it, this is the output of EMEs. And notice how it looks different now, right? So it's saying for potassium rate equals to 0, here are the 3 means of the nitrogen rates. For potassium rate equals to 30, here are nitrogen rates, and for 60 as well. So now there is a structure in place. And the way this is different is, even though the means themselves are probably still the same, but the difference now is that if you come on the COD, when you get the pairwise comparison and you run it, now this is how it looks like. So now you're basically only comparing the 3 nitrogen rates within a given potassium rate, meaning that this A has nothing to do with this A. or with this A. They kind of reset the lettering at each level of potassium. Okay. Now, if for some reason you are interested in looking on the other way around, potassium rates inside each nitrogen rate level, you just flip this order, right? So I would just say potassium rate, vertical bar, nitrogen rates. And then you print it. So notice again that you create this structure on the EMEans level, but it really has an impact when you call this the COD function. Because that structure you created on EMEans trickles down to the comparison that you're making. So now that I flip the order, now I have inside each nitrogen rate the comparison among the 3 potassium rates. And again, this A here has nothing to do with this A and has nothing to do with this A. When we did everything against everything else using the colon, yes, everything there was comparable, right? Now the comparisons are restricted to be only within a given nitrogen rate. So why is this important? Because the way you extract your means and the way that that trickles down to your pairwise comparisons should be reflected on how you explain your results, right? So if my goal here it would be this, I'm really only interested to know how potassium rate comparisons are within each nitrogen rate. I really don't care about how 60 potassium here compares to 60 potassium on a different nitrogen rate. If this is your question, if this answers your question, you will hopefully make a plot or a table that is intuitive with what you're doing. And we're going to talk about this in a second. And also that you're going to explain on when you interpret your results, that you take this into account when you explain that this letter separation was done this way on your captions, on the legends, and so on, right? Because it is different, right? Let's say, well, I guess for now, I'm just want to come back here and change to everything versus everything else. So you can just go there and replace the vertical bar for the colon, make sure you run it, check that your RCBD means all have no structure in them, and that carries over to your COD function. Right? So now all the A's here are comparable, right? Regardless if it's nitrogen or potassium inside of one or the other. Now everything's at the same level because I used the colon structure within them. Yes, Rick here.
Dr. Bastos, so what if the interaction effect is not significant, but the main effects are significant? So does it make sense to do the all combinations of pairwise comparisons that we are doing in the first code chunk in here? Or can we just go?
So if your interaction is not significant, but your main effects are, then you basically are going to do something like this. And then you do that like one chunk for potassium, another chunk for nitrogen. Right?
Correct. Yeah, that was my understanding.
Yeah.
Thank you.
Awesome. Thanks. Okay. So I want to move on here. Let me see. Let me look my cheat sheet to remind myself what I was thinking on this next chunk. Okay, right. So our final goal, we're going to have a publication ready plots at the end of this exercise is coming up soon. We're going to have to do some light wrangling for that. My goal with that publication ready is, as I was telling you earlier, we're going to have the box plots showing the raw data. And then we're going to bring in the letter separation that we just created here as our statistical summary of that raw data analysis. So we're combining both raw data to give some indication of the variability around that and also our pairwise comparison results. So for that, we're going to have to do a little bit of a wrangling here because so this RCBD COD all, which has the letter separation, this object, I mean, I'm not even sure what's the class of it. It is not a data frame because, I mean, it looks like a data frame on the first part of it, but then it has some text afterwards. So this in itself is not a data frame. I'm just going to get the class of it just to check. Yeah, so it says a summary EMM type of object in a data frame, but it's not fully a data frame by itself at that level. So what we need to have is we need to have a data frame. We need to basically turn this object, RCBD all, into a data frame where we can have the potassium rate, nitrogen rate, the EM means, which are the means we're going to plot on our publication-ready plots, but especially the letter separation, right? This is what I want to show in the map. This is where it is. I want to, share with you something that I think when I found out about this CLD function, I was so thankful for this, because when I took my first stats course using SAS, I don't know, maybe there was a better way, but at least the way I was doing that, I was taught, at least in that class, was you would ask for a pairwise comparison table among all these treatments. And then you yourself will look into those p-values and say, okay, potassium 60, nitrogen 0, the p-value of that compared to potassium 0 and nitrogen 0 is less or greater than or lower than 0.05, and then you would do the separation by hand. And I don't know, maybe there is a better way of doing that in SAS, but that's how I learned. I've seen some faces here like nodding along, so maybe I'm not the only one on this. So if you've never done this in SAS, you know it is so painful, it gives you a headache, and you probably made some mistakes on the way. CLD does all that for you effortlessly, right? So it is a big deal of having an easy function that can do that for you. So, we do want to show those letters in our plot. So we're going to have to basically transform this object into a data frame that we can then bring into ggplot. So that's what I want to do next in this wrangling chunk here. So I'm starting with RCBD COD all, which again is where we have all those pairwise comparisons. To transform this into a data frame, we're going to use a pipe and call function s.data.frame. If you just run that and you print it, now it becomes a data frame that we can bring into ggplot. ggplot takes data frames, right? So that's what we're after here. And then if you click on that right arrow, we're going to see the letters right there. Now, one thing that we're not seeing here in this data frame, but I will tell you it is there, is the default in CLD is when it gives you the letter separation, it's kind of stacking letters, right? So we have all the A's on the first position and all the B's. So we can see that it's stacking things on a way that the letter E actually has a few or a handful of empty white spaces until it gets to it. When we transform to a data frame, it does not seem like that's there, but it still is. So whenever we add these letters to ggplot, it's going to be, like when you give E, is going to be like a lot of empty space and E on that plot. So it looks weird, right? We want to remove the white space from the plot. So after this as data frame here, I want to do exactly that, remove that white space that I know is there. So I'm going to give this a pipe. We're going to use a mutate. I want to create a new column called letter. And this column called letter, we're gonna call a function called trim_ws, which stands for trim white space, and give the current column name .group. That's where our letters are. So this, if you run it and then you print it, here you're not gonna see a difference. But when we get to the plotting stage, I will show you with one and the other, and you're gonna be able to see why we're doing this step. And then finally, I just want to, if you remember on our initial data frame, we had this column called treatment name that we created by hand by combining both potassium and nitrogen. I just want to do that again here. And you're going to see why when we make the plotting. So let's just give it a pipe, another mutate. That was called TRT name. And the way that we created this treatment name is we use a function called paste 0. So paste 0 can take, if you're giving it a value that's stored under a column, you just give the column name. So I want this to be nitrogen rates underscore kilograms per hectare. And then if you want to give it a constant value or a constant string, we add a comma open and close quotation marks, and give that string here. I just want this to be a plus. And then we add another comma and give potassium rates as the column name. If you run this and then you print it and you inspect now your treatment name column, it basically took the number of the nitrogen rates, added a plus, the number of the potassium rates. That's what it did for us, like we did before already. Okay.
Dr. Bestos.
Yes.
So we're putting a period in front of the group, like we're putting a dot. So for the trim WS function,
Mhm.
we're putting a dot in front of group. Can we just say it group?
Try it out and let me know what happens. So
Okay.
I'm going to try on my side as well, but so something, I do encourage you all to do is you're not going to break the code. I mean, it may not work, the code may not work, but I do encourage you to play around with things like that and kind of try to, by trial and error, perhaps learn what is going on. So if I just said group, right? If I run this, okay, it threw me an error. So it's saying that object group was not found. It may not be the most intuitive error message, but if you go, whenever it says something was not found, is probably because either you forgot to create that object or you have a spelling error. If we check the column or if we check the pipe flow until here, so right before we go into where the error happened, and you inspect your data frame, the column name is dot group. So that's why we're saying dot group here, is because the column name is dot group. Does that make sense?
Got it. Thank you.
Awesome. Thanks for care. All right. So now we have our data frame with our potassium rate, nitrogen rate, mean, our pairwise comparison, letter separation, and then a treatment name column that we created here. I'm going to save this, and then we're going to get to our last chunk of this exercise, which is our final plots. So there are different ways of making this final plots. I'm going to show you one of them. I encourage you to think about other ways that you could show this. And then we're going to talk a little bit about how your plot design choices impact how your audience will interpret your plot. And this is important for you to think when you're making your own plots, but also to think of it when you are reading a paper of someone else that you may not know fully what they did, and keeping this in mind. All right, so let's begin here. My goal is to create a plot that I show raw data and also the letter separation along with it. So let's begin here with our ggplot. Up until this point, we've been only using, I believe this is true. I think we've been only using one data frame for our ggplots, right? And in those cases, we give data equals data frame name at the ggplot level. In this case here, we're going to use two data frames, one with the raw data and one with the pairwise comparison. So two different ones, right, for different reasons. So we're not going to specify data frame at the ggplot level. Instead, we're going to specify data frame at the geom level. So if you give that right there, the first thing I want to do here is to show the box plot of the raw data. That's the first layer I want to have. So there is a function called geom underscore box plots. We've seen that before already. So here I'm going to say data equals to, and I want somebody to help me out here. What's the object we're looking for here? What's the name of the object that we already created that we're looking for to show the raw data?
RCBD underscore DFW.
Yes, RCBD DFW, right? So RCBD underscore DFW. If I just print that, so you see what it is that initial, well, the data frame that we wrangled, but it's still the raw data with 36 rows. So that's what I want to show first. We're going to give a comma here. I want to break line just to make it easier. Let's call the AES function to establish our X and our Y. So when we were doing EDA, we did put, I think, nitrogen on the X and then we faceted by potassium or the other way around, don't remember now. We could do that. That could be something that we decide to do. But here, what I want to do first is not have the facets. So having all 9 treatment combinations on the X-axis. For that, we created this column treatment name. So I'm going to come here and say X equals TRT name. And then on the Y-axis, we're going to put yield, right? Yield KGHA. If you run this, this is what you're going to see. Let me see if I can review the code a little bit and you can see the output. This is what we're going to see. So let's say if I wanted to change the fill of these box plots according to that, to the treatment name as well. How would we do that?
Color equal treatment name.
Okay, so Amandeep here said fill equals treatment name, and somebody online, I'm not sure who, maybe Shakir or Umar?
Yeah, I said color equal TRT name.
Okay, so we could try both actually, and maybe we can understand what's the difference there. So it has to be inside AES, right? Because we're mapping an aesthetics to a column. So let's say here, let's start with color. So color equals TRT name, TRT name. If you run that, then the outline of the box plots is what we're changing. If instead we set fill instead of color, so fill equals treatment name, it would be the inside color of the box plot. We can change both if you wanted. You could do fill equals treatment name, color equals treatment name. It would change both and it would match them, right? So if we do color and fill equals treatment name, then it looks, yeah, maybe we don't want to do that because it kind of takes away what happens inside the box plot. But you know, you could assign the color to one variable, the fill to another one, if you think that can help you to show 2 variables in your plots. For now, I'm just gonna keep only the fill equals treatment name. So we should look like this. All right, so the other thing that we could do here is add the actual points behind this box plot. In this case here, we just have 4 points, so they're basically going to be on top of the box plot lines. So it's not like it's super extra information. But if you have more than 4 points, you know, it may, or more points in general, it could be good for you to show. So I'm going to add a plus. We talked about using geom point. So geom point as the point exactly where the point is, according to the X and Y value. Geom jitter gives a little bit of a jitter on the points. In case you have overlapping points, geom jitter helps you to remove that overlap. So geom jitter, I'm gonna go kind of fast here, but data equals the same as before, right? So RCBD underscore DFW. AES is going to be the same. So X equals TRT name, Y equals yield, kilograms per hectare. Now I come outside of the AES here. I'm going to give a comma and break code. And I want to say, I want to add some transparency. So I'm going to say alpha equals to 0.6, where this value ranges from 0 to 1. 0 is fully transparent, 1 is fully solid. So if we add that, this is what we see. Finally, I want to color those points according to treatment name as well. So I'm going to come here and say, let's see if it's color or fill. Let's try it. Let's try color equals treatment name on the geom jitter. Okay, that kind of worked. So that's, yeah, I'm going to call that good for now. Okay. This is our raw data, right? We're showing our raw data. Now we want to show the statistical outcome of this analysis, which is coming from the ladder separation, right? So we're going to add a string. It's not going to be a number is going to be a string. A, B, C, D is a string. Because we're adding a string, we're going to call the geom underscore text. There is a geom text, there is a geom label. I want to show you text first, and then we'll change to label, and then you see the difference. Yep. Scroll down. Yep. All right, so here again, we're gonna have to specify the data. Now, can somebody that has not helped yet tell me what is the object that we want to say here on data? Sorry, somebody said something?
Letter.
The letter, okay, but what is the object name?
RCBD CLD selected.
Yes, Priscilla said that. Was that Comfort? No, Charishma.
Karishma.
Thanks, Charishma. Yes, so this is the object that has the letter, right? So we're gonna call this data set. Notice that, if you did not notice, the data set on geom text is different from the one on the two previous geoms. So you can either define one data frame on ggplot level or geom specific data frames as we're doing here. All right, so I'm gonna print here RCBD CLD selected below so we can take a look at it. Let's call our AES again. Now our X is going to be equals to trim and name, right? Trim and name. What column do we associate with the Y axis? EME, right? This one. So notice that even though this is the yield mean, but the way that the EME function gives you the column is it names it as EM mean. So if we just said here yield kilograms per hectare, it would not work. It would say this column does not exist in this data frame, right? And that's because that's right. This data frame on the geom text does not have yield. It has EM mean as the column that has the yield value. So exactly right. We would say Y equals EME. And then this geom specifically has an extra AES argument that we can change, which is label. So that's when you say what column here has the actual value I want to add as a label in this plot. Let me just break line to make it a little bit more interpretable. So we're going to say label equals to, let's begin with the dot group, which is the one that we did not trim white space. I want you to see what happens there. So this is how that looks like. Maybe it's going to be even easier for you to understand if we change the geom slightly. So as I was telling you, we're using geom text. There is a geom label as well. And the main difference is that geom label adds like a background color behind that text, which I normally use label actually. So let's just for now change geom text. Instead of that, we say geom label. So if you run it, this is our label. You can see that white space is trickling through on that dot group column that came from CLD, right? However, if you remember, we did create a new column that we named letter that basically removed the white space. So let's specify the label to be equals to letter instead. When we do that, then the white space goes away. Okay, let me see here, what else I wanted to do. Yes.
Can we add end caps for the box plots?
Oh, give me just a sec online. Yes, Charles.
For example, for the CD, where we can even see the plot, like the box, is there in a way that we can adjust
The size? Yes. So Charles asked here, like for the case of the CDE, we cannot even see the box plots. Can we adjust that? Yes. So what I a lot of times do here is, I mean, you could, so outside of AES, there is an argument for size. I don't know what's the default size. Let's try 1 and see if that goes, if it increases or decreases. Okay, so it decreased a lot, too much. So we can play around with the size here and maybe that would help. I just changed size to 3 and it seems like this is a little bit better. The default on the geom label is is to have the amount of padding that you're seeing around the letter. So the label actually having that amount of padding. There is an argument that I normally change, I think is like label dot, perhaps it is padding. That we need to use a function called units, and then we can say, let me see what was the default. My select, I think it was 0.25 lines. So maybe let's try to use 0.1 and then lines. Let's see if this helps. Yeah, so this basically decreased the, how much outwards that label was going. It kind of shrinks. So the default is 0.25 lines. I changed to 0.1. Maybe you can change to 0.01 if we wanted and make it really tight. So a couple ways to fix that, right? So changing the size of the label or changing the amount of padding around the label. I'm going to keep 0.1. We had a question online?
So can we add end caps for the box plots?
I'm not sure I know what you mean.
You know, the end point and beginning point of the box plot, I'm gonna put a horizontal bar, like an error bar.
So you're saying you want to put like a bar going across the box plot with min and max?
No, for each box plot, I wanna, the 0% and 100% of the box plot, I wanna put a little cap
This
over
is
there.
minimum and maximum. Like,
I mean, I'm not sure if I'm fully understanding, but that is already where the point is. Right? Like this point is the minimum and this point here is the maximum of that box plot. And the same here and here.
Yeah, so I found a function, it's called stat underscore box plot,
Mhm.
and geom equal error bar. So it puts the
Oh,
error bars.
gotcha. Yeah, so there is a geom error bar as well. I believe you have to calculate the error yourself and then provide like mean plus error, mean minus error for that. That could be something you could show, but we're already showing the raw data. So, I mean, I wouldn't add an error bar here just because we're already showing the raw data to give that dimension. And error bars start getting more complicated to interpret, really, because I mean, error bar is a general word and it could mean a lot of things, right? It could mean an error bar could be mean plus or minus standard deviation. It could be plus or minus standard error. It could mean plus or minus CV, other things, right? So error bar in general, I think it adds more complexity than it helps explain, in my opinion. So I would rather show the raw data like we're doing. That's everything about this data. We're not summarizing the raw data in any way with the box plots. And then showing, I mean, we are summarizing with the box plot, but we're also showing the points behind the box plot. And then we're showing the letter separation. I think I would recommend that. But of course, you do what you want.
Thank you.
Yeah, thanks, Shakir. All right, so we are going to, let me see here. I'm going to make some changes here a little bit faster just so we can get through this. But I do want you to keep thinking with me. If my goal is to make this publication ready, there are many things that make this not publication ready. First one that I want to change is the axis of the axis title of both treatment and yield. So I'm going to come here, call the function labs. We've been using this already, so I hope you remember. I'm going to say x equals to, and then the way that I'm going to label this is to say N rate plus potassium rate in kilograms per hectare, because that's what the label means, right? This is the first number is nitrogen rate, the second is potassium rate, and they are in kilograms per hectare. I want to give a comma in here and call the y-axis. I want to rename that to yield in kilograms per hectare. So if you run this, now we see that our axis titles have been updated. The next thing I want to do here is I want to change the colors. So this is what I guess this is what I meant when I wrote the assignment, when I wanted to say change the fill scale. I want to tell you what I was thinking, and perhaps it's gonna make more sense now if you did not understand the first time. So, and this was a question I think I got it by email as well. So somebody was saying, should I change the scale fill function or should I change on the AES itself? So if you're changing the fill scale, it is on the scale fill function. So the AES is just determining what aesthetics is connected to what column variable or column name. That's what aesthetics is doing. And then it gives you a default, right? So let's say if we change the fill, it's going to give us a default fill scale, which is this. This is the default in ggplot. So when I ask you to change the fill scale in this case, you do have to first set the relationship between fill in a variable in AES in at least one geom. But then to change the scale itself, it would be through the scale underscore fill, and then there's many options there. Again, I want to call varieties in this case here D for discrete because we're coloring by treatment name, and treatment name is a discrete variable. Just to make sure that we keep our consistency with making colorblind friendly plots. Now notice what is really interesting here is that we changed the scale fill. We have not changed the scale color yet. So now the box plots fill was changed, but the color of the points was not. To fix this, you're basically going to have to call this again, but instead of saying scale fill, you say scale color. Varieties D. So now both of them have been updated to the variety scale, both the fill and the color. All right, one thing I want to do here, aesthetically speaking, or on a plot design side, is we really do not need this legend here because this legend is basically the same as what we have already on the x-axis. Yes?
You say again, why did you choose breed E? Because I had trouble with that in this yesterday, like remembering which ones.
Yeah, so if you choose the wrong one, I think it's gonna tell you,
Yeah.
right? But so when we are typing here, there's gonna be B, C, and D. These, so it says here as well, if you forget, I mean, you have to remember, right? I remember because I've used a lot of times, but D means that is for a discrete variable. So discrete would be like a factor variable, categorical variable. In this case, treatment name is a character variable, right? So it's a discrete variable, A, B, C, D. Now, if you have a continuous variable, then you have two options. You can use the C, which stands for continuous. So let's say, I mean, in this case, it's hard to give a very useful example because we do not have another continuous variable we could use here to show. But let's say that you wanted to show if the variable you're coloring by or filling by is a continuous variable, you will use C, which then gives you the whole spectrum from yellow to purple in a continuous way. And the B stands for bind. So it is also for continuous variables, but instead of having a continuum spectrum, it would basically have bins of values and assign a color to them. So let's say on the bind, you may make a bin that says, well, if, well, again, we're not calling by a continuous variable. So in this example, doesn't make sense. But let's say that we're coloring by yield, for example, and we use the C, then each yield value is going to have a very unique color in that spectrum if we use the C because it's continuous. If we use bind, it's going to take, let's say, values from 2 to 3,000. Those continuous values are going to be bins into one color. So it creates bins on a continuous space. That's the difference there.
But it's like out of that whole list on scale color, green, the only one that we can.
No, I mean, we can use any, right? I mean, if you just check all the ones here, you can play around. Some of them are for continuous variables. Some are for categorical or discrete variables. And if you play around, it's going to yell at you saying, you chose something categorical for something that's continuous, that's not working. And there's really more so these are all coming from ggplot. There are other packages that basically the function of those packages is just to expand these options with more scales, right? So there's some packages that have scales based on like TV shows. So there's like a Simpsons color scale. There is a Friends color scale, So there's really a lot of things you can explore. And these are the options that ggplot2 gives you, but you can explore more. You could just Google like color scales in R, something like that. Yep. All right. So I was telling you that really this legend here is redundant because we have already those treatment names on the x-axis. So I just want to remove the legend. There's a few different ways we could do that. I want to show you one that we're going to call the function theme. So if you want to select a different theme that changes a lot of things directly for you, you would do theme underscore something, right? So you had an assignment on this. I think you played around and you maybe found one that was your favorite. But if you want to change one particular thing about this theme, you have to be on the function theme no underscore, like what we have here. So here we have an argument called legend dot position. And then so here we could say right now the position is right. If I wanted this to be on the bottom, I'll be with you, Tifton, just a sec. I could just change legend position to bottom. It takes the values bottom, top, left, right. You can also give a pair of coordinates using the C function. So if I want this legend to be at the 0.1 on the X, 0.9 on the Y axis, it puts that inside the plots at those. And then you can play around and make sure you place it correctly, not overlapping with anything. In our case, I just want to remove it. So I'm going to come here and say none. Yes, Tifton.
Okay. My question is about the scale color. Can you advise somebody to do it manually? Maybe set parent equal to use the C function and you complete all the code for the color parents.
Yes, Paulie, that's a great question. So one of the options here is scale color or fill underscore manual. So if you have a set of values that you want to give, you can just come here and use the manual one. It has a values argument. Then you use the C function. You can either give the name of the colors or you can give the hex value, which sometimes I give the hex if I have it. Because if I'm changing manually, it's because I want a very specific color, right? So in that case, you may have the hex value of the color, which is going to do that for you. Yeah, so this is how you could do it. The only thing is you need to make sure you're providing enough colors to match the number of levels you have on the plots.
Okay, thank you.
Thank you. Okay, maybe let's see. Maybe we'll go just 3 more minutes to 10:50, and then we'll take a 5-minute break. Okay, so to me, I mean, we could make this plot better, different. We could change more things about it. For now, I'm calling this good, aesthetically talking. And I want to bring the point here of plot design. The more I learn ggplots, the more aware I try to become about my choices when I make plots. So for example, choosing a colorblind safe color scale is one of them. Showing raw data and statistical data together on the same plot is another one. Sometimes if you're writing a paper, you may have 3 figures that have a different response variable, but always the same treatments. I try to make consistent my color scale choice across all figures, so it's more intuitive for whoever is reading. So the easier you can make it for somebody to read it, the easier they're going to interpret, understand, and hopefully use your paper, cite your paper, and so on. So I try to be aware of my decisions when I make plots. I'm still learning, improving things every day, but I try to at least think about my choices. And one of them here comes down to the letter separation, right? So right now, we did compare everything to everything else. So a plot like this makes sense. Now, I want to make a change on my side. If you do not want to do that on your side, you don't have to, because I don't want you to have the wrong code. If you do the change, remember to change back to what it is now afterwards. So I want to come back here and let's say that I am unaware of this. and I do potassium rates inside nitrogen rates. Right, so we know that we have that structure, we know that the means are being, so nitrogen means or potassium means are compared with inside of a given nitrogen rate, but they're not compared across. So this A here, I cannot compare this A to this A. They are not together in the same comparison. And then I, make everything else the same. I make the same plot as well, and then I come out with this plot. Bad, right? Bad design option, bad design choice. If you are actually interested in showing, I think we did potassium inside nitrogen, we need to be mindful of how we show that to make sure that something is not misleading. Because here, I mean, first off, so we have nitrogen, potassium. So we're on the x-axis, the titles, the 0 is nitrogen, 0 potassium, 0 nitrogen, 30 potassium. And I'm comparing nitrogen inside potassium in my letters. So it's even more complicated to even make sense. I mean, I would never do this, right? This is just hell to whoever is trying to interpret, including yourself. So if I wanted to actually show that, how could we fix this? How would you make a plot that is better designed to show, if you wanted to show, in this case, again, comparing potassium rates inside nitrogen. Let me write that down because I'm going to forget. So potassium rates inside. If this is what you're trying to do, if this is your goal, how would you change these plots to make it more intuitive and more connected of what you show with what you actually did behind the scenes?
I think we'll use facet grid.
Okay, yes, was that Omar?
Yes.
Yes, I agree with that. And we had a couple comments here in Athens as
I
well.
was gonna be the same exact thing, just facet by nitrogen.
Okay, facet by nitrogen, is that what you're gonna say? All right. Good. I'm glad that you're all thinking along these lines. So, okay, so let's do that. I'm just gonna follow what you're all gonna tell me, and we're gonna try out. So let's do a facet grid by dot tilde n rate kgha, and just connecting that with the plus so it finishes with the theme.
No, we need to change the x to potassium rate.
Yes.
Otherwise, it's gonna give us the.
Absolutely. So then we would come here and we need to fix our x. So our x is going to be potassium rate, kilograms per hectare. We have to change that everywhere. So on the jitter, on the box plot, and on the label. Right? So, I mean, you still have to explain to your audience how things compare, but at least now is not completely messed up, misleading, right? Now we have a structure, a visual structure that is telling you how the comparison should be interpreted, right? So again, being mindful of first, what is your question? What is the type of comparison you need to make to answer your question? Perhaps you do want to compare everything against everything else, perhaps not. It comes down to your question. And then how you show that, how that structure of your question trickles down to your means, to COD, and then finally on the way you show your plot. Right, so all that is important to be aware of. Okay, so well, let me give you a break. Yeah, I get excited and I keep going. I forget to give you a break. So let me give you a 5-minute break. We'll come back at 10:57, sort of, and then we're going until 11:30 today. You just YouTube. Oh, sorry, I was looking at the chat. Yeah.
So when we were like originally, I think it was when we were looking at like CLD function, for looking, like when we specified to look at like that specific interaction between the two, the K rate and the message rate.
Mhm.
If we had like, let's say a lot of variables, how would we like include more? Like we want to look at an interaction over like 4 variables. Would we just like do a colon between all of the variables and list them? Or?
Yeah, so I mean, you can list as many variables as there were in your model, right? And you're gonna follow the same idea of if you want so let's say if we had, well, so let me repeat the question. So the question here by Zach in the room was if we had more, so if our model had more variables, let's say, I'm gonna give an example, fictitious example, that if we had a potassium rate as well, and there was the three-way interaction was significant, right? How would we specify that? The same concepts apply. So let's say if you want all comparisons of all rates of potassium, nitrogen, and phosphorus, so it'd be a P rate. I'm just gonna make that up. We don't have that. In this case, if you want everything against everything else, you just keep adding colons and following the variable name. It gets complicated very fast because, so if with a two-way interaction, you have 3 ways of showing it. With a three-way interaction, you have many more, right? And let's say if whenever you have more than a two-way, so in this case, a three-way interaction, even doing all the possible pairwise comparisons, of course, it depends on the treatment differences, on the area level, on the complexity of the experimental design. But sometimes I've done something like this, and then I'm down to the letter Z, and I'm like, okay, this does not make sense, right? I want to think of a better way of making these comparisons that is meaningful to me, and it doesn't add the whole alphabet to the screen, right? So then you start thinking, okay, so let's say if I was interested in doing potassium, all combinations of potassium rate and nitrogen rate within phosphorus rates, you could do that. Or really any combination of variables and colon or vertical bar, you can do that, right? As you said, you could, well, I guess you didn't say this, you said using colon, but let's say if I use the vertical bar everywhere, then you would be creating further structure of like only comparing nitrogen within 1 rate of potassium and 1 rate of phosphorus, right? So it's really up to you, to your question, and what structure is going to help you to answer your question. Okay, so yeah, so a big wrap up of all this entire exercise is this workflow, and I want you, as we increase complexity of experimental design analysis, I do want you to notice that this workflow will remain very similar. Like we're always going to load packages, bring data, EDA, wrangling, perhaps another set of EDA, modeling, checking assumptions, extracting model means, doing pairwise comparisons, doing a final plot. That is the workflow that we're always going to do in this class, and likely you will do something very similar to your research as well. You may have a few more steps, maybe you're going to have a few less steps than this, but the overall structure is not going to change much from this. So it's a good workflow, I guess, for you to try to begin your analysis if you need a direction, if you need a scaffolding for that. All right, let me see. I don't know if I had, I just had another piece of code here to export this to file. So if you remember, if you just come back to that last chunk, we're just gonna use a ggSave. I'm gonna open and close quotation marks to get the path. I want to get outside of the code folder, go inside the output folder. I want to call this RCBD _ means. You can just run that if you wish. Wait. Well, make sure that you run the plot as the last thing. So just rerun the plot and then run the ggSave. Still giving me, oh, okay, I made a mistake here and I just noticed what it was. So it's telling me I needed to supply a file name with file extension. I forgot to give the file extension. So I'm gonna get .png. That should work. Remember, another way on the question before about related to the size of the label overlapping with the box plot. So I showed you two ways of fixing that, changing the size of the label itself, or maybe the padding of the label. Also, another way of checking for those like size related things is once you export to file, check out that PNG on your file, because that you can play around with that as well. Right now, this is looking kind of ugly for me. I want to make it shorter. So I'm going to come here and on the GG save. The default was 7 by 7 inches. I want to have the height 4 and the width of 6. This is 2 inches. So we can run that again. Go to your output folder and reopen that file to inspect. Looks better now. If I change this for a smaller numbers, so let's say if I do a 2 by 4, it's going to further increase the size of everything, right? So changing things in ggplot directly is one way. Another way is for you, or both ways actually, is to also change the size of the file you are exporting, and that's going to have an impact on the size of your labels and text and so on. All right, so what we're gonna do now is I want to ask you to, if you have not done yet, go and click on that save button so all of your changes are reflected. We're gonna stage, commit, and push. So we stage our changes. I mean, you can stage all of them, so both the code and the output that we created. We click on that check mark. We're gonna give a commit message. So I'm gonna say finished RCBD exercise. You can commit and then push. So now all of your changes should be reflected on your GitHub repo, not mine. So you can check online as well on GitHub and see if that took place. Okay, so I know that some of you perhaps don't have the prerequisite stats course that maybe it would be better if you had to be able to fully understand what we talk about in this class. And so the next topic we're going to talk about is something that if you don't have that stats previous requisite, it may not be so clear. I hope that with the exercise it will help. But if you have taken a stats course, especially if you have taken an experimental design course, you've probably been exposed to the concept of fixed and random effects. At least here in Athens that I can see easier. If you're familiar with random and fixed effects, even if you have not used it, but if you're at least familiar with the concept, can you please raise your hand? Okay, we have a few people here familiar. All right. So that's our next point here. That's what we're going to do next. And we're going to start that off with a lecture to get everyone at least to the same page. And then we're going to run an exercise that we're going to talk more about that and implement a mixed effect model analysis. So once you saved your script, once you stage, committed, and pushed, you can just go ahead and close this RStudio. I'm going to go to the website, to our class website. I have a set of slides there for us. So it should be under the February 4th date. That set of slides is what we're going to be talking about today. All right, before I get started, anyone has any questions or issues with what we've been doing up until now? All right, don't hear any, so let's get started. Okay, so this next set of slides, we're going to be talking about fixed versus random effects. If you have not heard of these things, you are probably doing a fixed effect analysis. That's the default. That's where we start off. That's the simplest when we're starting to learn. So let's talk about those concepts and what they mean and what is the difference and how we implement those in R. All right, so our goals are going to be to talk about fixed effects and models, random effects and models, mixed effect models as well. And that's it. So up until now, so the CRD exercise, if you did that, and the RCBD exercise that we just finished, those models were fixed effect models. What do we mean by that? What does that entail? Basically, it means that your factors that you selected have systematic levels. For example, remember there is a difference here between factors and levels. Factor is nitrogen rate, level is 0, 100, 200, right? So our factors have systematic levels in the sense that we purposefully selected 0, 100, and 200 for a reason, right? We chose those values. Those are coming from us, from the researcher. We're telling I want 0, 100, and 200. That's systematic level. And therefore, our inference is about those specific levels, right? If you're doing ANOVA, analysis of variance, like what we did just before, I'm comparing the means of the 0 to the 100 to the 200 kilos of nitrogen per hectare. I don't have a 50 kilos. I don't have a 150 kilos. I just have the 3 levels I selected. So my inference is limited to only those levels if we're treating them as fixed effects, which most of the time is what we want with our treatment design. So let me take one, say again this phrase in a different way. Normally, most of the time, your treatment design variables, which are the ones that you select to answer your objectives, are going to be fixed effect for the most part. Not always, but most people, for the most part, your treatment design variables are going to be fixed effects because you want to know the mean response of those levels. In this way, by choosing those specific levels, you in the future, or maybe somebody else, can replicate the same study if they go and choose the same levels as well. And when we're treating things as fixed effects, like we've been doing up until now, we are interested in the population mean. We're trying to make inference on the mean response. I want to know, does the mean yield change from 0 to 100 kilos of nitrogen per hectare? The mean is our interest. So an example is basically what we've been doing up until now. We have specific rates of potassium or nitrogen and trying to assess the mean effect of that on yield. So fixed effect models, which again is what we've been doing up until this point, they only contain fixed effects. So we're just interested in the mean. They only have one source of variation or error. If you remember the model specification, you may not remember because it's like a whole bunch of mathematical formula, but we only had one sigma on that whole. So we had like y, so our yield is just explained by the overall mean plus the block effect, plus nitrogen effect, plus potassium effect, plus interaction effect, and the error. And on all those effects on RCBD, the error is the only one that has an assumption associated with it. And if you remember, the assumption is that the mean that is distributed normally, and that the mean is 0 in sigma and the standard deviation of sigma e, I guess, or sigma square e, depending on the formula. So that sigma there, that the standard deviation is the only source of variation on a fixed effect model. One source of variation, fixed effect model, only one source of variation. In that case, if in R, we can use the function LM if we're running a fixed effect model. The function LM only handles one source of error or variation, which a fixed effect model only has one. LM works well. If you've been working with SAS, this would be the equivalent of, you know what? I'm actually forgetting. I haven't used SAS in a while. What is the simplest proc again?
Prog GLM. Prog GLM.
proc GLM, is that, yeah, so proc, yeah, I don't fully remember this, but I remember there's proc mixed and there's proc mixed and proc, the three ones that I've used to use when I use SAS. But anyways, I'm not going to be able to tell fully, but in SAS, there is one option that is equivalent to LM in R, which is basically an option, a proc that only treats, only has one source of variation. That's the variation of your residual error. So proc LM, proc GLM. Yeah, so maybe proc GLM. So this is the formula we're talking about. So a fixed effect model, in this case here, I'm showing you Yij is the ith observation on the jth replication and the ith nitrogen rates. We have the mu is the overall mean. Alpha I is differential effect of the ith nitrogen rates. And then we have Eij is our residual that is corresponding to the jth replicate and the ith nitrogen rates. The only source of error in this model, this is a fixed effect model, is the distribution of that error term. So Eijk is distributed identically, independently, normal, with a mean of 0 and sigma square E. Only error source is the one related to the error itself. All right, so that's what a fixed effect model would be. If you all of your terms in the model are fixed effects and only source of variation is your error. With random effects is a little bit of a different story. So this would be vectors with non-systematic levels, meaning that those levels are a subsample of a larger population. So one example here that, I mean, it doesn't happen in practicality, in practical terms, but it would be perhaps an example that connects with our case study, is let's say I was not interested in the effect of any specific rate of nitrogen on yield. I just wanted to know the overall effect of a larger population of nitrogen rates on yield. So nothing specific, just overall. You would take a random subset of the nitrogen rate population. So let's say that your population is basically ranging from 0 to 300 kilograms of nitrogen per hectare, and you randomly select 5 numbers out of that distribution. So maybe you end up with 1.2 and then 53.45 and 281 point something, right? So random values, random from that population. So they're non-systematic in that sense. And you do that because your interest of inference is at the population of levels as a whole. You're not interested in just a specific level. You want to know how the overall behavior of that entire population of nitrogen rates has on yield in this case. And because of that, you may not be able to recreate those same levels in other studies because they are random. Also, the key thing here is something would be random if you are interested in the effect of those levels on the population variance, not the population mean. If you want to compare means, they have to be fixed effect. If you're interested on the variance, you may treat them as a random effect. So again, the shift here from an inference on means to an inference on variance. A great example here that I think it may make sense to you is years, sites, or blocks. This is a great discussion because, so for example, if you're used to doing experiments out in the field, for example, and you may have 2 sites, 2 years, and then it comes down for you to analyze your data, and then you're thinking, should I treat years and sites as random or not? I'm going to have some examples here of when you would do one and when you would do the other, but these are things that you could, if they could be treated as random, depending on your question, and they could be treated as fixed as well, depending on your question again. One that is very common that I found myself a lot of times thinking about this is you're going to find papers that people publish an RCBD analysis that, and when they explain how they did it, they may tell you like, the treatment factors of nitrogen and potassium were treated as fixed and the block effect was treated as random. So block, similarly to year and site, is one of those things that could be treated either way, depending on what you decide and perhaps if you follow some guidelines. If we just take one step back and think about it, normally a block, the way that we do blocks on the field, they're normally not a random sample of a larger population of blocks, which would be something that you would say, okay, I go out to this whole farm and I have this potential 50 blocks I can randomly pull from, and I pull 4. That would be perhaps a random treating blocks as random from the perspective of selecting them randomly. We normally don't do that. We just say block 1, 2, 3, 4 because they're side by side, because they're blocking for a reason. They may be separating soil types or something else. So anyways, I just wanted to perhaps start this conversation with that. So in random effects model, the model only contains random effects, meaning that now it's going to have more than one source of variation or error. You're not just going to have your residual errors, you're also going to have an error associated with a random effect. In R, there are a couple of packages, or I mean, more than a couple, but the most popular ones is they're going to be a couple of packages you can use to analyze random or mixed effect models, which is going to be the package called LME4, and the function is called LMER. There's another package, NLME is another package that we can use with the function name LME. So they're all kind of similar, but this is just one example. So LMER can handle multiple crossed and nested error terms or random effects in their associated variance terms. All right, so let me show you now a model, and I think now you're gonna see one difference here between the fixed effect model, and in this case, I think it's going to be a fully random effect model. So we still have our observation of yields. Mu is the overall mean. On a fully random model, the only fixed effect, in fact, is the overall mean. That's the only thing. You may have a lot of other treatment factors on that formula. If they're all random, the only mean you're getting out of this model is the overall mean. And then everything else is going to be variance. In this case here, alpha I is the random effect of the ith nitrogen rate. We still have that residual error, always have that in every model. That's our residual corresponding to the ith or to the jth replicate with ith nitrogen rate. But then we have more than one source of error. In this model here, we have 2. So we have the error associated with our random effect. So notice that before we only had this statement here, the EIJK, which is your residual that every model has, including fixed effect models. We only had this last row where the distribution of your residuals is IIDN, independently identically distributed normal, with a mean of 0 and a sigma square E as the variance or standard deviation. Now we have the same assumption or the same statement also for your random effects. So every model has a residual, even fixed effects. So random effect also has the residual, but now it has also the distribution of the error around the random effect itself, because now you don't care anymore about the mean of the nitrogen, the mean yield effect of the nitrogen rates. You want to know the variance of that population step. This has implications. Now, where this plays a role is the error of the model. Now, when you make comparisons, when you try to evaluate p-values, is going to be based on this formula. So now the error of the sigma square of any observation, before it was just the sigma square of E alone. Now it's going to be the sigma square of your random effect plus the sigma square of your error. So this is where a random effect model plays a difference compared to a fixed effect. It's going to change the way that the error of the model is calculated. And again, if you're changing how the error is calculated, you're changing everything except means. So means may still be the same, but all the errors around those means are changing, which is going to impact the p-value of ANOVA, is going to impact the p-value of pairwise comparisons, which will impact the lattice separation that you get in the end. So changing the error structure, which is what we're doing here, trickles down to every comparison you make in this model. So the The sigma square A is that group variance that's going to be attributed to variability between nitrogen rates. And nitrogen rates, because in this example, I treated nitrogen as a random effect. And then you always have the residual variance that's attributed to variability within the nitrogen rates, or pretty much the residual of the model that's left over. All right, before, well, I guess finishing here, one part of this conversation, which is methods to estimate variance components. This is something that is more complicated than I'm going to tell you here. I just want you to be aware of some of them and what we're going to be using. So there is still the ANOVA type 3 sum of the squares or methods of moments. This can be used to estimate various components for random effects. It's based on mean square decomposition. Again, we talked about this when we saw that ANOVA table on the lecture for RCBD. I did not show you formulas, but we just talked about how to calculate the mean squares being the ratio of or the mean square being the ratio of the sum of the squares of that factor divided by the number of degrees of freedom. This can, because the way it is estimating a variance component, it can give you negative estimates of variance, which should not happen. A variance should be a positive number. And therefore, this method is not the most appropriate to when you have random effects or mixed effects for that matter. Another method here is maximum likelihood, or ML. It basically maximizes the likelihood function. Again, this may not make any sense to you at this point, and that's all right. And it is known for underestimating variance, which means it's adding a bias to it. When we get to the conversation between how we decide between fixed or random for things that can be considered one way or the other, I will bring up this underestimation of variance again. And then the third method is restricted maximum likelihood, or RAML. This is the method that LNER, the function we're going to be using, uses by default, and it is the recommended method to use to estimate the various components coming from the random effects. So it maximizes the residual likelihood function after removing the fixed effects from the model. So it takes into account fixed effects first, and then calculates the various components of the random effects. By doing that, it produces unbiased estimates, and therefore it is our preferred method, especially if you have unbalanced data. So this is the key to keep in mind as well. Okay, so then let's see how much time I have. 4 minutes. Yeah, we're not going to finish this lecture today. So let me see how many slides we can go without. Okay, maybe let's go a couple more slides. We have time for that. All right, so when should I treat a factor in my analysis as fixed or random, and why? So I'm going to ask a few questions for you to consider. Are you interested in specific levels of that factor? So I want to know nitrogen 0, 50, 100 specifically. If the answer is yes, then you should treat it as fixed, as we've been doing up until now. Up until now, we ran only fixed effect models. Are you interested in using the levels as a sample of more levels from the larger population with the goal of assessing variability and not mean effects at the population level? If you say yes to this, you may treat as random, but you have to check a few more boxes. And so if you say yes, if you're interested in just using some levels to serve as a sample from the larger population of levels, because you're interested on the variability and not the mean, and were your levels randomly selected from a population of potential levels, like you were saying with blocks, right? With blocks, they're not really selected from a population of blocks. We just have them side by side. It's not like you had 50 of potential blocks and you randomly picked 4. And you have sufficient number of levels between 5 to 8. Then you can treat it as random. Why is this here? So the minimal number of levels between 5 and 8 is basically because it is harder to estimate variance components reliably than it is mean effects. So it's easier to get a pretty good idea of the mean of that population with just 4 replications, for example. But it's really hard to get a good idea of the variance of the population with only 4 reps. You need at least 5, the more the better. So if you only have 4 levels, you know, I mean, you can still do as random, but it would not be recommended. So again, if you're interested in the variability and the levels of that factor were pulled randomly from a larger population levels, and you have a lot of levels within that. So let's say I'm interested in the variability of the blocks. I don't care about the mean of the blocks. I pull my blocks from a larger population of potential blocks, and I have at least 5 blocks. Yes, then you could treat as random following these guidelines. So this is the reason for those is because reliably estimating a variance component requires more data and more replication than estimating means. If you have low level of replications on these levels, then the variance estimates would not be accurate, which may be best to just treat that as a fixed effect instead. Classic example here is blocks in an randomized complete block design. Should you treat as random or as fixed? People do either way. People publish either way. We're going to see this in an exercise. What are some of the implications of doing one or the other? I'm going to stop right here on mixed effect models, so I don't rush you. Is the attendance issue open already? Okay, so claim your attendance. We're going to finish this lecture on Tuesday and then do an exercise that we're going to treat blocks as fixed as we've been doing and as random. And then we're going to compare them side by side to understand what are the implications of doing so. Yeah, so that's a wrap for today.
RCBD assignment.
Oh, yeah. Okay, yeah, so we do have an assignment due today. Make sure you submit that, and if you have any questions, let us know. Remember to use GitHub. I know a lot of you are already using. Thanks for that, and thanks for everyone that is helping others as well. I appreciate you all helping each other and seeking help on GitHub. Yeah, I think that's it. Let me stop recording here.